Okay, so there are three main goals when you're setting retail electricity prices. And that is that they're supposed to cover a utility's fixed costs, especially debt repayment on infrastructure. They need to cover the variable or fuel costs. So put those two together, that need to cover the utility's operational costs. And they also have to return, or they're supposed to return or cover return on equity for shareholders. So utilities, whether it's a retail distribution utility that's participating in a deregulated market or a regulated market like we have in North Carolina, set retail prices in conjunction with utility commissions, which are the main regulatory bodies that oversee electricity pricing for consumers. And the process through which utility commissions set prices is called a rate case. And rate cases are generally forward-looking, which means that utilities have to, and utility commissions have to estimate what the cost of service is going to be in the near future. So what do you think the biggest sources of uncertainty are in the cost of service, the cost of providing people electricity? So for example, if there were a rate case this year in North Carolina with a decision that's needing to be made being the fair price of electricity in North Carolina, and that being based on what the cost of providing electricity to people in North Carolina is going to be next year or the next 2 years. What sources of uncertainty do you think could impact what that cost is? So let's take a look. Here's a sort of a hint. Here's the least cost dispatch schedule. We've seen this a couple times. This is the optimal least cost way of meeting fluctuating electricity demand. But just looking at this, what do you think could be a driver of cost uncertainty here? And there's a couple different things to look at here. So one would be the cost of fuel. Right? We've already sort of talked about how the cost of electricity from a coal plant or the cost of electricity from a natural gas plant are directly influenced by the cost of coal or the price of coal and the price of natural gas. And in particular in this table, what I've shown is that the price of natural gas, at least historically, has been somewhat volatile. There have been periods where it's really been really very low, and we're in one of those periods now, at least as of 2019. And then there have been other periods where the price of natural gas is much higher. So the price of fuel can certainly influence what the cost of providing electricity could be as well. Other things could be the available supply of both hydropower and wind and solar. These are variable renewable energy sources, and there is interannual variability, which means one year you might have a lot more than another year. So the main three things that can impact the cost of providing electricity, for example, to people in North Carolina from Duke Energy's perspective would be demand. So higher demand means a higher cost of service. Fuel prices, so higher fuel prices mean a higher cost of service, and the availability of renewable energies, in particular hydropower, but also wind and solar. So less renewable energy means higher costs. So when utility commissions set retail electricity prices, they use a typical rate-making formula. And what this formula does is it establishes a target level of revenues that the utility needs to meet in order to both cover its costs and also make profits for shareholders. And so the easy equation here is R equals C plus V times R, where R is equal to the utility's target revenues. That's how much money they would like to earn next year by selling electricity. And what that amount of revenues are going to cover are C, which is the utility's total cost of service, so their operational costs. So fixed costs, which would include fixed operations and maintenance, the cost of keeping the lights on, as well as debt repayment on all their their mortgage payments, plus variable costs, where variable costs are basically fuel costs. And then what we also want revenues to cover here is a quantity which is the product of V times R. So V is the depreciated value of the utility's infrastructure. So in other words, it's how much all their stuff is worth. And R is the rate of return for utility shareholders. So what we're saying basically is that we want revenues to equal the cost of service plus some sort of reasonable profit. where the reasonable profit is described as the product of V times R. And the rate of return is the percentage profit rate that they're going to make. But note that what we see in this rate-making formula is that the amount of profits that the utility can make is not based on how much electricity they sell. It's how much their infrastructure is worth, because that represents the investment, the previous investment that shareholders have made. So technically, retail utilities can only make a profit on their shareholders' investment in infrastructure. They don't, again, make a profit on the actual sale of electricity. So let's think a little more deeply about this. What do you think that this incentivizes utilities to do? If they can make profits as a percentage, only as a product of how much infrastructure they own, what do you think this encourages utilities to do? Well, it encourages them to build more stuff. And this can be somewhat controversial. So a lot of times utilities will come out with a plan to improve the grid, right? And we have a similar initiative happening in North Carolina where Duke Energy wants to spend the next 10 years strengthening North Carolina's energy grid, modernizing it. If you listen to the radio, NPR, sports radio, every once in a while you'll hear these ads talking about how we need this robust, resilient grid. And this effort will make it easier for Duke Energy to integrate renewable energy. And I think there's a lot of truth to that. There's also truth to the fact that when they are planning to spend $13 billion in improving the grid, that infrastructure becomes part of what's called their rate base, which means it's that V, it's the value of their infrastructure that becomes the basis of their profit margin, right? So as V grows, their target revenues increase as well, and they can technically increase prices on customers in order to earn a profit on that investment that their shareholders are making. So this is a somewhat controversial topic. So let's do an easy example using this equation, R equals C plus V times R. So let's say the question is, how much revenue does utility need if its annual fixed costs are $50 million? And again, that $50 million amount would represent all the debt repayment, the mortgage payments the utility has to make on its infrastructure, as well as fixed operations and maintenance costs. Its annual variable costs, which are basically the fuel costs, are $35 million. Its infrastructure is worth $250 million. And its regulated rate of return, this is the rate of return that the Utility Commission will allow it to make on the depreciated value of its infrastructure, is 7%. So we can do the math here. C, the total cost of service, or the operational costs, are just fixed costs plus variable costs. So we have $50 million plus $35 million gives us 85. The depreciated value of its infrastructure is currently worth $250 million. And R, the regulated rate of return, is 7%. So we can say R is equal to C plus V times R is equal to $85 million plus $250 million times 7%. And that gives you a final value of $102,500,000. Right, so this is the target revenues. This is how much money the utility needs to make selling electricity in order to both cover its costs and earn 7% rate of return for shareholders. So if the revenues have to be equal to $102,500,000, how do we determine? How do the utility commissions determine what price to sell the electricity at? So the simplest possible answer would be to just say that the price is equal to our revenue target, how much money we need to make, divided by how much electricity we expect to sell. So let's assume that total demand for electricity for the entire year is 1.37 billion kilowatt hours. That's how much electricity we expect to sell over the next year. Then we could say that the price is just equal to how much money we're trying to earn, 102,500,000 divided by 1.37 billion kilowatt hours. And our volumetric price here is 7.48 cents per kilowatt hour. However, it's not that simple in practice. So let's take a look at why. There are a couple different parts of electricity bill. If you're in the very, very simplest case, there might just be two, but in reality, there's a lot more. I'm simplifying things here. But in general, there are sort of two different categories of charges that you'd see on an electricity bill. The first would be fixed charges. So a fixed charge is a sort of a fee that helps utilities recover fixed costs of serving a customer, including meter reading, billing, and administration costs, etc. Volumetric charges are charges that accrue proportionally with the amount of electricity that a customer uses. And so there are different types of volumetric charges. There can be flat or time of use rates. So a volumetric charge that's flat would just say for any given customer, for every kilowatt hour they use, they're going to pay 7 cents, right? And a time of use rate means that during some times of the day, the volumetric rate of electricity might be 2 cents per kilowatt hour, and other periods of the day, it might be 9 cents per kilowatt hour. So here's an example of a time of use pricing scheme for Southern California Edison. This is a big utility in California. And at the top, you see the time of use pricing for the summer. And at the bottom, you have time of use pricing for winter. And there's also a difference between weekdays and weekends. So just in general, electricity demand is higher during the weekdays and lower on the weekends. And it's also, in California especially, higher during the summer and lower during the winter. And you can kind of see this reflected in the time of use pricing. In general, the summer days have higher electricity prices than the winter days, and the weekdays have higher prices than the weekends. But let's just take a look at the summer weekdays. We can see there's 4 colors here, and each one of the colors has a different electricity price in terms of cents per kilowatt hour. And there are 4 different periods of the day. There's the 8 a.m. to 2 p.m. And if you use electricity during that period of the day, and you're assigned this time of use pricing rate or scheme, you're going to be paying 26 cents per kilowatt hour. And then between 2 p.m. and 8 p.m., you're going to be paying 46 cents per kilowatt hour. And then again at night in the evening from 8 p.m. to 10 p.m., you're going to be paying 26 cents per kilowatt hour. And then late at night and into the morning, 10 p.m. to 8 a.m., you're going to be paying 12 cents per kilowatt hour. So why would a utility, or why would a customer even, want to use time of use rates? Well, the advantage for the utility is that it allows them to charge customers prices for electricity that more closely mimic the prices that they experience out on the wholesale market. So remember, if we're thinking about the role of Southern California Edison here, at least as a retail distribution company, they are these green bubbles in the middle, right? Utility One Retail Distribution Company. What they're doing is they're buying electricity from the wholesale market, and they're paying a wholesale market price that goes up and down all the time because that price is driven by market economics. You have a system supply curve and demand, this perfectly inelastic demand curve, shifting left and right. And as that happens, the price of electricity increases. And so a time of use rate allows that retail price that the utility retail distribution company is charging its customers to reflect that same sort of natural variability. And so the end effect is that their finances sort of line up a little better. In addition, it does send retail customers a price signal that they might use to modify their behavior. For example, if a utility retail distribution company is having to buy electricity for a really expensive price in the middle part of the day because demand is really high, they might want to be able to pass that signal on to their retail customers who may, if they experience a higher price during the middle part of the day, use less electricity. So, for example, this figure, and we've seen this before, shows wholesale electricity prices in California for 1 week in the summer of 2010. Right. So, if you are a utility and you're experiencing this, but you're not passing this signal on to customers, and what your customers actually just see is a flat rate. For example, they're paying 5 cents per kilowatt hour during the during the day, no matter what time of day it is, then they really have no incentive to change their behavior. But if their retail customers do see this fluctuating signal, and it's a lot more expensive to buy electricity in the middle part of the day than it is during the night, then you might think twice about when you're drying your clothes or running your dishwasher or running your air conditioner. So we will revisit time of use rates later when we talk about renewables, because they could be an important part of dynamic demand side management, which is just a way of saying changing the way consumers behave when they're using electricity in order to reflect the natural availability of wind and solar throughout the day. So we have two parts of an electricity bill: fixed charges and volumetric charges. So why use a combination of fixed and volumetric charges? Well, so let's think about that. What if we just used fixed charges? Let's say that we're all customers in North Carolina, and Duke Energy just charged every single customer a single amount of money every month, $100, for example, to be connected to the grid, and then you could use as much electricity as you wanted. So that might allow Duke Energy to recover its costs, or at least have a stable source of revenues. But what do you think would happen? Well, there would be no incentive for people to conserve electricity. If you're going to pay $100, whether you use 5 kilowatt hours versus 5,000, you might as well use as much as you want. And so there would be no incentive for people to become more efficient. And then it would also end up charging people on a per kilowatt hour basis. The people that use less electricity would actually pay more per kilowatt hour than the people that use more, which is not what we want to have happen. The other alternative is if we just use volumetric charges, right? So if there were no fixed charges and we all just got charged, 5 cents per kilowatt hour for electricity, well, what would that do? So let's go back to our previous example where we're looking at how much revenues a utility would need to make in order to cover its costs and make a profit for shareholders. So we're back to this rate-making formula where it's R equals C plus V times R. Again, R is utilities' target revenues. C refers to the utility's total cost of service, so fixed and variable costs. V is the depreciated value of the utility's infrastructure, and R is the rate of return that they are able to earn on the shareholders' investment in that infrastructure. So in the previous example, we were trying to calculate how much revenue a utility would need if it had fixed costs of $50 million, variable costs of $35 million, infrastructure worth $250 million, and a rate of return of 7%. And what we decided is that they would need to earn about $102 million, $500,000, and that if they expected to sell 1.37 billion kilowatt hours, the simplest way to price electricity in terms of a volumetric charge would just be to say their target revenues, 102,500,000, divided by 1.37 billion kilowatt hours. And what you would get is a volumetric charge of 7.48 cents per kilowatt hour. So that's fine. But let's say, what happens if demand is temporarily, for 1 year, 10% lower because of mild weather? So we have a warm winter and a cool summer, and electricity demand is lower, 10% lower. So let's take a look at what would happen here. So some of these numbers would change. Our fixed costs would not change. Remember, the fixed costs are the cost of keeping the lights on, as well as paying the mortgage back and all the infrastructure. So that $50 million is going to stay the same. Annual variable costs, remember, are proportional to how much electricity you produce, which is effectively what your demand is, would change. So let's say if demand was 10% lower, then we're going to say annual costs are also 10% lower. So 10% of 35 million is 3.5 million. So we can say that the new variable costs, when demand is down 10%, are now only 31.5 million. And the infrastructure is still worth $250 million, and we can still earn a rate of return of 7%. So we actually need to recalculate how much revenues we need to cover our costs and earn a profit for shareholders. Because if our annual variable costs are lower, we actually need less revenues to cover our costs and earn a return for shareholders. So we can recalculate that and say R is equal to C plus V times R. C here is the only thing that changes. It goes from $85 million to $81.5 million. V stays the same, it's $250 million, and then our R stays the same as well at 7%. And our new value of big R, the target revenues, is $99 million. So that's how much we need to earn in a year where our demand is 10% lower. So let's say that actually we don't change the price of electricity because this is an unexpected change in demand. So we set the price of electricity at $7.48 per kilowatt hour based on the expectation that our demand was going to be 1.37 billion kilowatt hours. And so even if demand is lower than that and our target revenues decline, the price that we're charging customers is actually going to stay the same. So we're still going to charge customers 7.48 cents per kilowatt hour. But our actual revenues here are going to be 10% less, right? So we're still going to charge 7.48 cents per kilowatt hour, but we only sell 90% of 1.37 billion kilowatt hours, and so our actual revenues are $92,228,400, and our target revenues were $99 million in order to earn a rate of return for shareholders, and so. What that means is that we're 6.8% short on revenues. So our actual revenues are 6.8% less than our target revenues. And so we don't have enough money to both cover our costs and allow shareholders to earn a return on the 7% return on equity. So now let's assume that there's a fixed customer charge in place that allows the utility to recoup 25% of their target revenues no matter what. So we actually need to recalculate retail prices in this case because we don't want to collect the total cost of service plus the profit for shareholders just using a volumetric charge. We only need to cover 75% of that using a volumetric charge because 25% we're just going to get by having customers in our system because we're just going to charge them a flat rate to be connected. So the new volumetric charge is going to be 75% times our target revenues divided by demand. And so we're going to still assume that total demand for the entire year is 1.37 billion kilowatt hours. And so our new volumetric charge is 75% of our original target revenues, so 102,500,000, divided by our expected demand, or 1.37 billion kilowatt hours, and we get a volumetric charge of 5.61 cents per kilowatt hour. So for our target revenues, in a year where demand is lower, is $99 million, and we're actually selling electricity for 5.61 cents per kilowatt hours, and we're actually only going to sell 90% of what our expected sales are, or 1.37 billion kilowatt hours, and we're adding on to that this charge that we're getting from all the customers, right? We're charging each one of our customers a certain amount so that we cover 25% of our target revenues in an average year. Right, so 25% times 102,500,000. Then our actual revenues are 94,812,000, and so that means we're only 4.2% short on revenue. So we still are not where we want to be. We're not meeting our target, but having the demand charge in place, or the customer charge, allows the utility to earn money no matter how much electricity they sell, is one way of protecting against these unexpected downturns or years when demand is particularly low. So utilities use a mixture of fixed and volumetric charges, and that's because if you use all volumetric charges, it leaves them a little bit too exposed to losses of demand. And if they use all fixed charges, it doesn't encourage any sort of energy conservation. But still, most of utilities' annual revenues come from the volumetric sales of electricity, which means essentially that their money still depends greatly on demand for electricity. And so, in many cases, what this means is that customers still have a financial incentive to reduce their dependence on utilities by, for example, becoming more energy efficient or adopting rooftop solar. So, what is the downside of this model? What's the downside of having utilities who still earn their money by selling electricity at a volumetric rate? Well, we've seen this in the past. We've seen instances where utilities, where their finances are dependent on selling electricity, that can cause problems. Remember in the 1970s, when utilities built too many nuclear power plants, so they had they really high fixed costs. A lot of that was associated with mortgage payments on these power plants, and then demand did not increase as quickly as much as they thought it was going to. And so what happened is that they had to raise prices. Lower demand can cause financial problems. They had to raise prices in order to both cover their costs, which were dominated by fixed costs associated with mortgage payments on nuclear power plants, while also being able to make a reasonable profit for shareholders. So, how could this happen again in the future? Well, we're getting, I want to reference quickly one of my favorite topics, which is the utility death spiral. We're going to talk about this later, but the whole idea here is that customer adoption of both energy efficiency and rooftop solar could erode the demand base, the customer base for utilities, leaving them with less and less demand for electricity and needing to cover roughly the same amount of revenues and costs. So the only way for them to get around having less demand while still making the same amount of money is to increase prices. And that's it, sort of initiates this positive feedback that then makes it more likely for customers to go put solar on their roofs, which makes utilities increase prices even more, and so forth and so on. So we'll have a whole lecture about this later in this class.